Wow, that picture doesn't really look like me. I'm not sure where we got it. Anyway, good morning, everybody. I hope everybody is enjoying the talk so far. I particularly like Anand's information. He taught me something I didn't know. I had no idea Merck was 300 plus years old. That is the opposite of my startup. We're 2 years old. I also really enjoyed the slides from SK Hynix. They're going to actually make my slides look really bad because their slides looked fantastic. So I live in San Francisco. I'm coach of my 6-year-old's soccer team. I tell that team 2 things before they start each game. 2 things that I want to tell you. The advice I give them is please go out and have some fun. The second piece is try to learn something new. So if I have one ask from this audience today, those 2 things is what I'd love. I'd love for you to have some fun, as much fun as you can have during a chiplet talk, and I would like you to learn something new. My name is Sean Lundy. I run sales and business development for a Silicon Valley-based startup called Eliyan. So the goal and the focus of our company is die-to-die and die-to-memory PHY IP and chiplets. That sounds like a lot, but it's actually very focused on one thing. So as chip designers, architects, there is a lot of options available today. So trying to figure out which option makes sense, what trade-offs, what pros and cons are available, we're going to dig into that a little bit, specifically from a die-to-die and die-to-memory perspective. That's the goal. But before we do that, I want to start with a little game. So the game is easy. We're going to play a yes or a no game. So if the answer is yes, you're going to put your hand up. If your answer is no, you're not going to do anything. So I'm going to visually assess your answers. The first one is easy. And thank you, Anand, for not talking about AI, because everybody talks about AI. I'm actually going to talk about AI. So first question, remember, yes or no? Who knows what AI is? Hands up for yes. Okay. That's a significant amount of people. That was just a control, by the way. I expected to see a lot of hands going up for that one. Okay, second question. Who knows or has heard of chiplets? Yes, hands go up. No, stay down. Okay, great. So, I'm talking to an audience that knows what I'm talking about. Third question. Who has ever heard of my startup, Eliyan? Okay, great. That's absolutely 0. That's good. We're a brand new startup. We only came out of stealth mode probably a year ago, so I'm not surprised. That said, we are working with all the great semi companies in Korea, but we'll learn more as we go. All right, let's get started. So sometimes before we can decide where we're going, we have to actually look back and see where we came from. And in this particular graph, we're looking at performance over time, probably from the 1950s to the present time. So before I was even born, I was born into the thing called single core era. What does that mean? Well, that's where we started. It was enabled by Moore's law and voltage scaling and increased clock speed. That era is over. So that probably went from the 1950s to the 2000s. When I started my career, I wasn't a sales guy. I actually was an analog IC designer. I designed PLLs and ADCs. When I started designing, that was in 2000, we were in 0.18 micron. That's 180 nanometers. So that was in 2000. Right now, our startup is taping out chips in 2 nanometer. So it's not that I'm that old, it's that we have progressed that much in that time frame. So the era that I started working in was the SoC. So that's the era that we're in to some extent today, but you can think about that timeline as somewhere between 2000 and where we are today. And again, SoCs rely on Moore's law. Everything relies on Moore's law. We'll get to where that's going soon, and multiprocessing. So that's SoC, system on chip. Honestly, when I started my career, I thought that was it. Monolithic SoCs, we're going to make them bigger, we're going to make them faster, and that's where we're going to end up. I was wrong. So I tend to gauge technology progress on conferences like this one. So when you go to a conference, there's always a buzzword. Obviously, Gen AI is the new buzzword, but that's kind of old news now. So back in 2017, 2018, I remember I was at a conference in San Jose, and I heard this word, and it was chiplets. And I was like, chiplets? What is a chiplet? It didn't make any sense to me. I was designing these huge SoCs, and people were talking about breaking them up and making them smaller. I'm like, why do I want to do that? So that was 2017, 2018. Intel and AMD started coming out with some products that had chiplets in them. So I was like, wow. I didn't buy into it. I kind of forgot about it. But that chiplet era is pretty much at its beginning. It started in 2017. People took it a lot more seriously in 2022. That's where it really started to grow. So the purpose of this particular slide, it's not to say that SoCs are done or monolithic design is done, but I would say they're coming to the end of their life cycle, which is the polar opposite of the chiplet era. We are just in the beginning, and there's a lot of untapped potential. So that's where we are today. So the other bit in this system in package, we'll explain that as we move forward. So the number one question that pops up is, where do chiplets fit? And it's really hard, again, not to use this word Gen AI, but Gen AI is really where they live today, and high-performance computing. But honestly, there is no vertical that you're going to be aware of that won't be touched by chiplets. There's very good reasons why all chip makers are moving towards chiplets, and we'll go through those reasons in a minute. But everything, edge, gaming, aerospace, industrial, there is no chip manufacturer, architect, ASIC designer that's not going to incorporate this modular-based system moving forward. So just for fun, this graphic, as you can see, my slides are from a startup. So we don't have professional content. Before I came here, I pulled open ChatGPT and I said, please generate me a graphic based on these verticals. And it spat out this graphic. That happened in 2 seconds. So this is the world we're in now. Things are evolving, things are moving. The graphic is not perfect, but the fact that it was generated in 2 seconds with no input from me except a text string, that's pretty incredible progress. So let's take a look at companies and products that you're familiar with that already use chiplets today. So the one on the left, I'm not going to use the pointer. I refuse to use the pointer. I think the pointer is for cats, and there's no cat on my stage, so I'm not going to start pointing. So I'm going to describe instead. So the NVIDIA H100, everybody knows what that is. So this is the Hopper GPU. So when you look at this system in a package, you see Hopper GPU in the middle, surrounded by 6 banks of HBM3 chiplets. So that first question I normally get is, well, why only 6 banks of HBM3? And we're going to get to the why in a minute. but it's limited by the packaging technology, which is advanced package interposer. There's ways around it, which we'll talk about, but for now we're just talking about who uses chiplets. NVIDIA H100. Of course, AMD came along recently and upped the performance of that, and they came out with something called an MI300. What is that? So this picture is hard to see it, but there's actually 8 banks of HBM3. And that's pretty much the max that you can put on an interposer today. 8 banks with 2 compute tiles in the middle. So this is very aggressive system in a package. Super awesome design from AMD. Really showcasing what chiplets can do. Again, AMD's EPIC. This one's a little bit different. So it's got 4 compute tiles with an I/O tile in the middle. Again, showcasing chiplets. Intel Sapphire Rapids, 4 banks of HBM3, 4 compute tiles. Lastly, obviously this is just a handful of examples. There's a lot more than this. AWS, this one's a little different. The one in the middle is the CPU. The 2 in the front are I/O, and the 4 on the side is actually DDR, so a different type of memory. No HBM in this one. But again, the point of this slide is to showcase the biggest companies in the world doing the most aggressive AI design are doing it via chiplets because they understand the value prop of that. So every keynote has to have multiple graphs. If you don't turn up with a bar graph, it's not a keynote. So these are my token graphs that I'm bringing to the party. So the first one highlights, well, we got 2 problems. Actually, we got 10 problems, but I'm giving you 2. So the biggest problem we have at the minute in AI, and this just doesn't hold itself to AI. This is everything. High performance computing, edge. We have this problem all over the place. So for decades, as long as I've been an engineer and way before me, the game was simple. Make the transistors smaller and cram as many of them as you can onto a chip. That's Moore's Law in its simplest form. And that was great, and that was very cool, and it worked fantastic, except until it didn't. So this graph on the left is showing you one clear thing. Moore's Law is slowing down. People will argue and say, there's a huge argument right now about whether Moore's Law is dead or not. I don't think it's dead, but this graph on the left shows you that it's slowing down. And honestly, it doesn't matter if it's dead or not. The fact that AI is driving such enormous demand for compute capacity and capability and energy efficient capability makes this a moot point. We're going to need something much more aggressive than Moore's Law. So the graph on the right is actually kind of interesting. It's comparing CPU, GPU performance against DRAM and interconnect bandwidth. And there's an obvious problem here. CPU, GPU performance is going this way. DRAM bandwidth and interconnect is going this way. So these 2 things don't make sense. When you have these 2 problems together, we got a problem. Moore's Law slowing down. AI HPC needs more aggressive DRAM, and it needs better interconnect, and the performance keeps going up. So I don't know how many people in this room know who Mike Tyson is. Does everyone know Mike Tyson, the boxer? Okay, Mike Tyson said something, and it's strange to quote Mike Tyson at a semiconductor conference, but I'm going to. Mike Tyson said this. He says, everybody has a plan until they get punched in the mouth. What has that got to do with anything? Well, our plan in semiconductors was Moore's Law. That was our plan for decades. Moore's Law will fix it. We're cool. We'll just get smaller transistors. We'll put more of them on. That's gone. It's slowing down. Gen AI HPC's demand is going up. So we need a new plan What is the answer? So Eliyan, and a lot more than Eliyan, believe that chiplets are a part of that answer. Not the whole answer. There's a lot more that needs to happen. But we think chiplets is going to help address a lot of this problem. So we've said the word chiplets a lot, but I haven't told you really what a chiplet is. So that's what we're going to do next. What is a chiplet? So at its simplest, you take a monolithic SoC, you modularize it into little blocks, you break it into pieces, you put that inside a package. You take a system PCB, you break that up and you put that inside a package. So now you've got this thing that's modular, chiplet-based system in a package. That's a lot of words for a simple thing like a chiplet. So let's just focus on one part of it, modular. The key here is modular. So the bullet point that I want you to really pay attention to is optimize processes per function. What does that even mean? What sort of a statement is that? So what that means is you're mixing and matching process nodes versus performance versus function. So imagine this. You've got a monolithic AI or high-performance compute chip. It has to be on the latest and greatest process node, whatever that is, 2 nanometer, 18 Armstrong, the most aggressive to get the most performance. But lots of things on that ASIC don't need to be in that process. There's no need for the memory PHY to be in 2 nanometer. It could be in 12 nanometer. So here's the beauty of chiplets. You break up the monolithic SoC and you take the parts off it that don't need to be in the latest and greatest process nodes. And the beauty of that is now you can keep your AI chip moving on the latest and greatest aggressive process node, but you can put other things on slower, cheaper, more cost-effective processes. And that's the key. But for chiplets to make any sense, the key piece is the interconnect between the chiplet and the package technology. And that's where our startup, Eliyan, come in. We focus on the interconnect. So the take-home here, the enabler for chiplets is the actual connectivity between the die. So another question that comes up a lot is, why aren't chiplets moving faster? The biggest hang-up we've had in the last few years is standards. Always standards. Standards always get in the way of stuff because nobody wants to connect something to proprietary links. They want everything to be standards-based. So the good news is standards have moved aggressive. UCIe has moved very fast. Bunch of wires, Bow 2.0, another great standard. These two on the right are actually proprietary standards from Eliyan. One called UMI, which is Universal Memory Interface, which we're pushing through OCP right now. So we're hoping to make this a standard. This last one, SBD. The point of this slide is the limitation in chiplet technology has been a lack of standards. Standards are coming and standards are moving fast. There's other things on this slide that I'm not going to talk about, I'm going to address later in terms of how it works. But really quickly, at a high level, UCIe is unidirectional. Bow is bidirectional and UMI is bidirectional. That will be important in 4 minutes from now. So there is a lot going on in this picture, and unfortunately I don't have a ton of time, but I want to spend at least 2 minutes here because this is important. So the picture that's in front of you is not how things work today. This is not what an ASIC looks like. Do you notice how little is on the ASIC? That is the key. Real estate on an AI or a HPC ASIC is precious. You do not want to put things on that ASIC that you don't need to. So here's what we're saying. Take everything off the ASIC that you don't need, build silicon-proven, memory-specific chiplets instead. So what we did in this picture, we took off the memory controller, we took off the DRAM memory PHY, and we put it onto a chiplet. Why? Because it saves real estate on the ASIC. And the real advantage here is that now, with one interface, UMI, you can connect to any memory you want. HBM, you can connect to DDR, LPDDR, GDDR, it doesn't matter. Silicon-proven specific memory chiplets. Now all you need is one interface on the ASIC, and you can connect to any memory interface that you like. And it comes with a whole host of other advantages. A die-to-die PHY is probably 10 times more efficient in terms of beachfront bandwidth than a memory PHY. A die-to-die PHY is also 70% smaller than a memory PHY. So you do not want that on the ASIC. So in this new brave world that we're describing, we're saying chiplets, silicon-proven memory chiplets, take it off the ASIC. It doesn't need to be on there. So this slide is overly complex for what it's saying. So it looks like I'm picking on UCIe. I am not. I am basically saying compare Eliyan's UMI to UCIe. By the way, our company have got UCIe PHYs as well. We love UCIe. We're a big supporter of the standard. But if you're an architect and you're designing memory or you're designing ASIC to ASIC, do we use the same PHY for both? You don't have to. In some situations, it's not a good idea to use something that's unidirectional that talks to memory. Why? In the history of memory PHYs, they've always been bidirectional. The way the ASIC talks to a memory is you can either read or write, but you can't do both at the same time. So that's where you need dynamic bidirectional. Imagine the case for UCIe. You've got 32 transmit, 32 receive. They're fixed unidirectional. Memory traffic doesn't operate like that. It's not 50-50. It's 60-40, 70-30. In the case of UMI, we can configure TX or RX to be either one. So I can have 64 TX or 64 RX. That's where you need bidirectional. Talking to memory, it doubles your bandwidth efficiency. We've talked about interconnect. Now I want to talk about packaging. What sort of packaging options and what's the trade-offs? So again, this slide looks like I may be picking on interposers, advanced packaging versus standard packaging. I am not. Our company does both advanced and standard packaging. But I do want to highlight and give you options. So the only point in these slides is that you've got a toolbox of options, and when you go to make your architectural decisions, I want you to pick the right tool. And it's not always a hammer. So in this case, interposer on the left, standard package on the right. Advanced package, standard package. So the big difference is the interposer limits how big you can build system in packages. As you've seen, AMD, NVIDIA have put 8 HBMs on a package. That's only because the interposer is for reticle limited. If you took the interposer away, you could build something that's got 24 HBMs. The other big thing about removing the interposer and advanced packaging is that it forces you to put the HBM close to the ASIC. That's not necessarily a great idea from a thermal perspective. HBM above 95C gets uncomfortable, whereas an ASIC can run much hotter. So if you have the ability to move the HBM away from the ASIC, your thermal challenge goes way down, no more liquid cooling required. Manufacturing, yield, cycle time, all terrible on advanced packaging. That problem goes away on standard. Last thing that I want you to think about is allocation, supply chain. Jensen Huang from NVIDIA sat down with TSMC executives last week to talk about one thing: supply chain. Where are we going to get more CoWoS? Where are we going to get more interposers from? Supply chain allocation is a real problem. Here's my second. I have to speed up because I'm running out of time here. This time is going very quickly. My other graph, all this graph is saying is compute costs is out of control. And the other thing it's saying is if you give me more bandwidth, more DRAM, my AI performance is better. So this picture is awesome. This picture says one thing. I took an NVIDIA H100, which you've seen in the picture. This is a cartoon. But NVIDIA did this study that said if you give me 2x HBM, 3x performance. Give me 4x HBM, 9x performance. That's not me. NVIDIA said that. So I was like, cool. I can build the picture on the right if you get away from interposer. I can put 24 HBMs with 2 compute ASICs on a standard package, and I can do that today. That's what we can do today. 2 times compute, 4 times more HBM, memory wall, I/O wall, gone. That's what we can enable. This is a pretty picture that explains the same thing. In my ideal world, this is where I want us to go. Chiplets for everything. Memory, SerDes, co-packaged optics. One interface around the ASIC, chiplets everywhere else. This slide is more for, well, I was going to take it out, but then I left it in because it says something, I think it says something quite important. It looks at the memory or the area profile of different forms of chips, interfaces. So the first one is the JEDEC HBM-PHY. Look at how huge that thing is. It's got 2048 pins, and it's got a profile of 26 millimeters squared. If you move to UCIe, it reduces that by half. If you move to UMI, it reduces it again by another factor. So this is saying, be very careful about the interface that you put, because it has a huge impact on real estate on your ASIC. And if you're a big company that's designing AI, you care more than anything about the real estate that's on that ASIC. So you need to think about, am I designing ASIC to ASIC, or am I designing ASIC to memory? And what interface do I care most about? What metrics are important? Picojoule per bit. Of course that's important. Power is everything. Terabits per second. Beachfront bandwidth. Yep. Standard or advanced packaging. UCIe, BOW versus UMI. It all comes back to performance over TCO, total cost of ownership. Actually, there is no right answer here. The right answer is it depends on what you're trying to do. It goes back to the toolbox. We've got a bunch of options. You have to pick the right tool for the use case. And it's going to be different for every customer, for every application. That's just the way it is. But the key is that you understand what options you have available. If you don't understand, you can't design the right choice. So I'm going to conclude by saying, I really do believe this. It sounds like it's a bit of a bold statement, but chiplets system in package is the future of semiconductors. All the big leading companies in the world are going this direction. They're going there for a reason. Power, cost, yield, cycle time, allocation, the list goes on and on. Existing die-to-die PHYs are unidirectional. For memory, I think we need to think about something that has been always used, bidirectional. Our universal memory interface gives you bidirectional, it accelerates chiplets, and most importantly, if you're AI, it eliminates and removes the memory and I/O wall. And that's huge. So I'm got 21 seconds left, so that's why I had to pick up my pace at the end there. I want to talk more, but I can't. But that's the Irish in me. We don't like to stop talking when we start. But I do want to say thank you so much for your time. I really enjoyed talking to you. I hope you had a little bit of fun. I hope you learned something new. And until next time, Kamsahamnida.